Hello, everyone. I'm Scott Grizzard. This is Calculus one for the date today, which is the whatever it is, the 20th of April. From the University of South Florida. This is the 11 o'clock stream. Um, Today, during the 9:30 stream, there were significant technical issues. Basically, everything that could go wrong went wrong. And well, not everything that could go wrong, knock on wood, did go wrong, but a lot of things went wrong. The tablet failed, the thing failed to sync, and I wound up switching to my third device in order to make this happen. And when that happened, the battery was drained on it. So now I'm flying a little bit. I've got I'm basically, the thing was a catastrophe, and everything broke. So what I'm doing today is I'm going to skip the one thing that you all probably want most, which is the quiz review. I'm skipping it. You may watch the 9:30 video. I am sorry, but it took me 45 minutes because of all the technical issues to get through the quiz. And now the 9:30 people have to watch this video in order to get the content of the class because of all the technical issues. So I think I've resolved most or some of the technical issues, but if they aren't resolved, this thing is going to go slowly because of the technical issues, and I want to make sure that I get through this material. Are there any questions before we begin? Obviously, if the question is something to do with the quiz, you're going to have to watch the video and then come to office hours. Any other questions? Okay, and I've got a TA in chat. Everyone say hi to the TA. And I am sorry that everything broke last time, but that means that we can't go over the quiz, especially that graph, which was very, very difficult. So if you want to go over the graph, please do the video, and then if first comes to shove, I'll go over it tomorrow. I'll make a video, and then Wednesday night, don't forget the problem set. Last week, no one showed up. Now I understand there was a Chem 2 exam and all this other stuff, but I am still doing the Wednesday night problem sets, problem videos. And right now, Discord says they're rolling out a new feature that'll let us all do videos together. If that isn't rolled out on our server by the time that Wednesday comes around, we'll do it on Teams, because Teams does support that. And there'll be less me talking and more you guys working problems again. Okay. So what we want to do is we want to talk about Riemann sums. So Archimedes had this idea that we went over last time, that I could take the area of something like a circle, and I could divide it up into little pieces. And when I divide it up into little pieces, I can get closer and closer approximations to what I'm actually doing. Okay, so if we look at that, right, we had this idea that what I could do was get closer and closer and closer and closer approximations of what I was doing. And then I would use little rectangles to discover that. So how do we feel about that idea intuitively, 1 to 5? Just the intuition about what we're going to do to estimate the area under the curve. All right. So we've got this idea. So what we're going to do is we're going to go from left to right. We're going to do the base point. And what we're going to do is we're going to fix x. So remember from the idea of the derivative, what we did was we took a graph, okay, and then we fixed x, and then we went to we fixed a particular x, and then we took the limit, right? So recall for a derivative, recall what we did here, okay? We wanted the derivative, we wanted to do f prime at a particular x. So what we did, it's not going to work, is it? Okay? I don't understand why it won't sync. It's actually plugged in. Okay, but for some reason it won't sync. Oh, there it is. Never mind, it is working. Okay, so remember for the derivative, what we did was we had a graph and we stuck a point. We took it at a particular x. So we stopped at a particular x, and then we had this idea of an h. Sorry, the tablet's failing again. I hate you. Okay, let me see if I can do it another way. Okay, so I need to reboot the tablet again. So I'm going to do it. I don't know why it keeps failing, but I'm going to show you this on this thing. So I had this idea. Sorry. In just a minute, I'm going to start writing on a sheet of paper and holding it up to the camera. Okay. So I had this idea that what I did was I had a particular x that I was interested in. In this case, x equals 5. Okay? And so what I did here was I got closer and closer. I fixed 5. I wanted to calculate f prime of 5. So what I did was I fixed x. And then, I'm sorry, f prime of 1. So, and then I let x get closer and closer and closer to 1. How do we feel about that? 1 to 5. This idea that what I did was I wanted to calculate f prime of 1. Okay? And so what I did was I fixed x at number 1, and then I took the limit of the tangent lines. Let's see. You got to be kidding me. Oh. Don't switch. Close Discord. I already turned you off, and for some reason it won't stay off. Quit Discord. I don't want you to update. I don't want you to talk. Okay. I hate Windows. Okay, so what I had was this idea, and what I did was I fixed x, and I took the limit. Okay? So if we see that again here, what I'm going to do, what I did was I fixed x, and then I took the limit of the secant lines. So I had a secant line here, and then I had a secant line here, and then I'd have a secant line here, and then eventually what I would do is I get secant lines that were closer and closer and closer to what I was talking about. Okay? And then I'd say, okay, now we're going to let the function run again. All right. Well, now I'm going to do the exact same thing, except I'm going to estimate the AUC function using this tracking. So I want to estimate AUC F0 of x. So what I'm going to do is I'm going to fix x. For this example, x equals 2. And then what I'm going to do is I'm going to take closer and closer and closer estimates of the thing I want to do. Okay? So what I want to do so I've got x cubed minus 2x squared plus 2. And my interval is I'm going to stop from 0 to 2. Um, okay, and now the machine that's supposed to do it for me isn't working. Great. So what I'm going to do is I'm going to do interval from 0 to 2. Okay? So here's what I'm going to do. I want to estimate using lower. Using 2 rectangles. And the issue is I've got a lot of choice over what my rectangles are. Okay? So, by the way, please ask questions. Are there any questions right now about what we're trying to do? And I can do this by using lower endpoints, upper endpoints, left endpoints, right endpoints. Okay? And I've got some choice. So we're trying to figure out, evaluate this thing when x equals 2. Using rectangles. Okay? Let's start with using right endpoints. Okay? So let's do right 2. And this is some similar to something that you did in peer leading last time. So what I'm going to do is I'm going to estimate the area of the thing. Okay. So for two rectangles, I'm going to use the right endpoint. So the first rectangle goes from 0 to 1, and the second goes from 1 to 2. Now, I'm going to use right endpoints, which means that my first one is going to be right here. Right? This is the right endpoint of this, so I'm going to call that the height of my rectangle. And this right here is my right endpoint on this one. So there's my second right triangle, right? I go all the way over here to the right, and I wind up at this point right up here. Okay? So the area of my two rectangles is going to be this area here and this area here. Okay? That's the thing I'm doing. How do we feel about this? 1 to 5. So the width of this one, so the height of this one is 1. Okay, so what I'm going to do is I'm going to do height of 1 times width of 1. So the height of this is f of 1 times the width, which was 1, plus f of 2 times the height. I'm sorry, times the width, which was 1. So the height of this first rectangle is f of 1, and the height of the second rectangle is f of 2. And what I wind up with is this is 1 times 1 plus f of 2, which is 2 for this case. I should not have done something that worked out like this. Plus 1. And that equals 1 plus 2, which equals 3. So that would be right 2. How do we feel about that, 1 to 5? Okay. Let's do right 4, because what I want to do is I want to increase the number of rectangles. That's the big idea. Okay? So the big idea is I'm increasing the number of rectangles. Okay? So that's the rectangle associated with using two, that's the number associated with using 2 blocks, and I wind up with the number 3. Okay? Well, let's increase the number of rectangles to 4. Now I got 4 rectangles, and I'm using right endpoints. Okay? So what I'm going to do is I'm going to do the exact same thing I did before, except now I'm going to use 4 rectangles. Give my computer a second to catch up. There it goes. Okay, so now I'm going to use 4 rectangles. Okay, so this is rectangle 1. This is 2. This is rectangle 3. Rectangle 4. Okay. This is right 4. So I'm going to go over to the right point. Right here is my first rectangle. Okay, I go to the right point, I go to f of 1, sorry, f of 0.5 times, now my width is 0.5, plus f of 1 times 0.5 plus f of 1.5 times 0.5 plus f of 2 times 0.5. Okay. By the way, if there are questions, please post them in chat as we go. I know you're used to me asking, and are there any questions about this? But I do have a TA now. Yay, thank you. Who can answer questions in chat while I'm talking. So don't feel rude to ask questions in chat. So now what I'm going to do is I'm going to compute f of 0.5. Okay. And then I'm going to multiply that by 0.5. Okay. Well, f of x in this case was x cubed minus 2 times x squared plus 2. That's going to be a fun number to compute. Okay. So I need to compute this. Fortunately, I don't need to because just a moment ago I computed it here. So what I'm going to do is I'm going to ask this, what is f of 0.5? And it is going to tell me that that is not there. 1.625. And while I'm at it, I'm going to ask it what, I'm going to ask it to times that by 0.5. And it's going to jump down because it hates me. Go away. So I get this number here, which is 0.8125. How do we feel about that? Where that number came from, 1 to 5. So I'm talking about that number right there. That's that estimate of that particular rectangle. Okay. Then I'm going to do it again, but this time I'm going to do it with 1. So the second one is f of 1. Well, f of 1 here is 1. I don't really need the computer to do that one for me. So this is going to become 1 times 0.5. This becomes 0.5. The next one, all right, everyone on board with that? Okay. The next one I'm going to plug into my computer. And what I'm going to get is 0.4375, approximately. And then the last one I'm going to plug in, and I'm going to get 1, because I'm going to wind up with 2 times 1. Is everyone on board with those numbers? 1 to 5. How do we feel about that? This right here is 2 times 0.5, which is 1. Okay. All right. So now when I add these three numbers together, I wind up with the approximate value of 2.75. And that would be the approximate value of the area of these rectangles. Okay. I add these three numbers up, I get about 2.75. If you don't believe me, check it after class. If you don't believe me, here, I'll show you on the computer. Here. And I wind up with 2.75. Okay. So that would be the right area estimate with four rectangles. How do we feel about that? 1 to 5. This idea, this process. I just took the area of the four rectangles and I added them together. Okay. Well, if I do this again, I'm going to wind up with something called right 8. Okay? So let's advance this one more time. And I wind up with 8 rectangles. And notice here what I did. When I did this, I go now to 0.275. I got here 0.5, etc., etc., etc. Okay? And each time I took the right input. So let's see if we can put a formula together. All right? If I do n rectangles, if I have n rectangles, what's my formula? Okay? So there's the question. Well, what would be my width? If I have n rectangles, what would be the width? Okay? Yeah, so x. Here it's going to be x, which is 2. Right? But it's 2 minus the other endpoint. It's really 2 minus 0 divided by n. However many rectangles I do, I'm going to take this interval, 2 minus 0, and I'm going to divide that through by n. Okay? So that's a very good answer. Now, how do I figure out the height? The height's going to be a little bit more tricky. Okay? What I'm going to do is I'm going to come over here and I'm going to call these things, I'm going to give them numbers. I'm going to call this one x0. I'm going to call this one x1. I'm going to call this one x2. I'm going to call this one x3. And I'm going to call this one x4. All right, which should not be confused with x. Okay, so here I'm going to wind up with what about these x's? Okay, x0 equals 0. x1 equals x0 plus the width. I'm going to call the width here, I'm going to call this change in x. I'm going to call x2 equals x1 plus the change in x. And I'm going to call x3 equals x2 plus the change in x, and so on and so on and so forth. How do we feel about that, 1 to 5? Okay. And then the height of each rectangle is f of xk. Right? I want the rightmost endpoint. So the height of the kth rectangle is going to be f of xk. Right? That's the y value associated with here. So in this case, for the 4, this x1 was 0.5, and I took f of 0.5. So what I have is that right in equals f equals, we'll change in x. I'd like to, so the height of this is f of x1 times the change in x, which is the width, plus f of x2 times change in x, plus f of x3 times change in x, plus dot, 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 plus f of x n minus 1 change in x, plus f of xn times change in x. For each of these, this is the height. And this is the width. This is rect 1. This is rect 2. This is rect 3. This is blah, blah, blah. This is rect n minus 1. And this is rect n. How do we feel about that, 1 to 5? So again, this was 8 rectangles. Now I go to even more rectangles. Here I've got 16 rectangles. Right? And I get another estimate. And then I go to more rectangles. Here I'll go to 6 rectangles and I get even more. I used 32 rectangles. I get another estimate. Okay? But this would be the general formula here for any number of rectangles. Okay? Now, I use this fancy sigma notation because I'm, cool. And I wind up with this fancy sigma here, which says that what I did was I took the sum starting from 1 to n of f of x1, f of xk times the change in k, where the change in x, where change in x equaled b minus a over, x minus a over n. And xk equals xk minus 1 plus change in x, and x0 equals a. How do we feel about that? That's the formal definition of the right sum for n intervals. And the only way to really get at this is to play with it. Okay, no one is responding to the poll. I'm going to assume that either nobody's watching or, yeah, I'm just going to assume nobody's watching at this point. Am I? Oh, good. Some people are watching. All right. Okay. All right. Well, if I wanted to do left intervals, okay, there's not a lot I need to change. If I want to do F intervals, It's still not doing the lowers. I don't know why. It's really making me upset. If I want to do left intervals, the only thing I'm going to change is that I use the left endpoint as opposed to the right. Okay? So this one here is left intervals with 2, and this one is right intervals with 2. Okay? How do we feel about that, 1 to 5? So I'm not changing anything except the fact that I'm going to use the left endpoint. Let's see what that looks like. Let's actually do that. Let's do the exact same thing before, but let's use the left endpoints. Okay. Now, it depends on the function. So the question is, do we always wind up with over and under estimates? We have no idea. Okay. But we're going to get to that. We're going to get a way to always get an underestimate and get a way to always get an overestimate in a moment. Okay. Because we do actually want that. Okay. But right now, we're not caring about where the estimate is. Okay. So let's do 2 left endpoints. Okay. So let's do this one here with 2 left endpoints. So now my rectangles okay, are going to be x1, x2, x3 as before. Okay. But now what I'm going to do, there's like a lot of lag between the two. I'm sorry about that. But now what I'm going to do is I'm going to use the left endpoint instead of the right endpoint. So on this one, I'm going to use this as my height. And I'm going to wind up with a rectangle that looks like this. And then I'm going to do it again, but I'm going to wind up with a rectangle that looks like this. All right. And I say this, and it's I don't know why it's lagging so badly today. It's like the internet hates me, but it does. I guess it's Monday morning. Everyone's online trying to get business done. There they go. So what I'm going to choose is this. I'm going to estimate this area right here and this area right here. So for this one, I'm going to wind up with my height being f of x naught times change in x plus f of x1 times change in x. Here, f1, f of x naught is 0 times 1, f of 0 times 1 plus f of 1 times 1. F of 0 in this case is 2. F of 1 is 1. And I wind up with 3. Okay. How do we feel up? How do we feel? How do we feel about that 1 to 5? Ah, that might be it. It might be the weather. Yeah. Okay. So all I did was I used left endpoints instead of right endpoints. Okay. So I took this big rectangle here and this big rectangle here. Well, it just so happens that on this particular function, the two wind up being equal. Okay? But that's not true once I start taking the other endpoints. So here, if I go here and I bump this up one, these endpoints here, the left endpoints become an underestimate. Well, the right endpoints are, under, basically somewhere here and an over. Okay? So as I increase the number of endpoints, but the point is that if I hit play here and go all the way to the end, and I hit on the right, and I hit here and I go all the way to the end, notice that this number and this number notice that these two numbers approximate each other. So when I start going here, I'm going to say that left end equals f of, now, I took the left endpoint instead of the right endpoint. Before I was taking a right endpoint, and now I'm taking a left endpoint. So what I'm going to do is f of x0 times change in x, nothing else changes, plus f of x1 times change in x, plus f of x2 times change in x, plus plus f of x n minus 2 change in x, plus f of x n minus 1 change in x. And notice I don't use f of n, right? That's the rightmost endpoint. But the other endpoints are all the same, basically. Just where the rectangles are flips. So this is the rect 1. This is rect 2. This is rect 3. This is rect n minus 1, and this is rect n. Okay? And then when I put it in fancy sum notation, I wind up with the sum as k equals 1 to n. Now here's the trick. Instead of using the kth endpoint, which would give me rights, I'm going to use lefts instead. So I'm going to use f of k minus 1, of xk minus 1, times change in x, where change in x equals x minus a over n, which is again the fixed x, where x0 equals a, and where xk equals xk minus 1 plus the change in x. Okay, so how do we feel about that, 1 to 5? Okay. It's the exact same definition, except that I'm using the left as opposed to the right endpoint. Okay. Now, I want to formalize what I mean by the area. So what am I going to do? I'm going to take the limit as n goes to infinity. All right. Let's do one more, though. Let's do lower and upper estimates before we do that. Okay. Now, does everyone remember this weird min function from before? So I had this function called the min function. Does everyone remember this thing? And it was this function that let me take the max over an interval and the minimum over an interval. Okay. Well, in order to do this for the rectangles, I'm going to basically do the exact same definition. Okay? But instead of using either the left endpoint or the right endpoint, I'm going to use the lowest point on the interval. So when I do low in, I'm going to wind up with right here, I'm going to take min of x of f x0 of x1 times change in x. So here instead, and this is going to be a little bit, I'm not saying this is the most beautiful definition in the world. It's a very complicated expression for an extremely simple concept, okay? It's a horribly complicated definition for a very simple concept, okay? So this whole bit about the min, going back to whether or not I have an over or under estimate. This whole bit about the min is that I'm going to take the lower one. Whatever the lower estimate is, that's what I'm going to take. Okay? So to start this off, I'm going to start here with 4 rectangles. Why is it moving? I don't want it to stop moving. Okay, there it is. I'm going to start here with 4 rectangles. And here, I'm going to take the minimal value for rect 1. Here, I'm going to take the minimal height for rect 2. Here, I'm going to take the minimal height for rect 3. And here, I'm going to take the minimal height for rect 4. How do we feel about that, 1 to 5? What I'm going to do is take the minimal height of each of these. Okay. And this gives me something a little different. The under and over estimates, I cannot control that when I do left and right. I can't control whether or not I get an overestimate or an underestimate. But here I can. The point is that here I can control what I get. Okay? So formally, it looks something like this. Okay? Formally, I'm going to call low n this thing. Okay? And then I'm going to call high n exactly what you expected that to be. And let's go ahead and put this in some notation. Okay. And this one's a little weird, and I admit it. Okay. But I want you to keep this in mind that there's this thing out there, right? I wouldn't ask you to compute this on the test. I might ask you to use it, but not compute it. Okay. And when I say use it, I mean like use it in a proof. Okay. But I want you to have a concept of that there is a way to always get an underestimate. Okay. That's the big concept I want you to have here. And then I'm going to define max the exact same way. Okay. All right. How do we feel about those two definitions, 1 to 5? This is a little strange, and I admit it. But again, think about the big concept. The big picture is this. The big picture is that I've got one that always gets me an underestimate, and I've got one that always gives me an overestimate. Okay? Don't get bogged down in the notation. It's very easy to see that sum symbol and get bogged down in the notation, and I don't want you to do it. Okay? I want you to stay a big picture. Don't get bogged down in the notation. Okay? You can do problems. That's fine. You'll do upper, lower, left, right problems. That's all great. By the way, on WebAssign, I meant to assign it for tonight. I didn't. There'll be 2 WebAssigns due tomorrow. Sorry, I didn't get it done. It's been a little bit hectic over the weekend with the whole what are we going to do about test 4. So I wrote test 4 over the weekend. We're supposed to have a meeting about it today. I don't know what's going to be the end result of that meeting because we had a test 4 at the beginning of the semester, but then I had to rewrite it. Don't ask. Oh, do ask. I mean, it's because of this whole mess. So we're trying to minimize the amount of things we're asking you to memorize for the test, not because we kind of just we want it to be more conceptual. So what we're doing, we had to rewrite it. So it is what it is. So anyway, just again, big picture. How do we feel about the big picture? 1 to 5. How do we feel about the big picture of this? What am I trying to do? I'm trying to get something that always gets me above, and I'm trying to get something that always gets me below. Big picture. I'm not so concerned about the little picture. I want the big picture. Okay? I want the concept. The concept to me is more important than the computations for this. So now what I'm going to do is I'm going to take the limits of this one. And notice that I've always got an underestimate for the top one, for low. And I've always got an overestimate for high. So now what I'm going to do is I'm going to take the limit of both. I'm going to take n as it goes to infinity and see what's going to happen. Okay? So, all right? So what I'm going to do is I'm going to take the limit as I go to infinity. Okay? So what I'm going to do is I'm going to say the integral from below from a to x of f of t dt equals the limit as n goes to infinity k equals 1 to n min fxk minus 1 xk times change in x. All right. That's what I'm going to call the lower integral. Okay. And then I'm going to do the exact same thing. But now I'm going to take the upper integral. Okay. Now, where does this integral sign come from? Okay. Recall dx dy. Oops. Okay. So recall that this was true. Did everyone remember about this? Okay. So here, oh, it's not synced yet. Okay, it's syncing. It's thinking about syncing. There we go. So recall that dy over dx was the limit as the change of x goes to 0 of the change of y over the change in x, right? So I used Greek characters for my non-limit case, and then I used Roman characters for my not. Okay. Well, here I have a sigma, so here I have a fancy s. Corresponding to my Greek sigma. That's all that means. Okay. If the lower equals the upper, then I say f is Riemann integrable. And AUC FA of x equals the integral from a to x f of t dt, which is the same as these two things. Okay, how do we feel about that 1 to 5? So all I've said, it's still working on the other pieces. I'll come back to it in a moment. All I've said is that if these two things, okay, if these two things go to infinity, if these two things approach the same number as my number of subintervals go to infinity, if these two things approach the same number as my subintervals go to infinity, then I say that that function is Riemann integrable. Okay? And I say that the area under the curve equals what that Riemann integral is. Okay? How do we feel about that? 1 to 5. Don't get lost in the notation. I cannot stress this enough. It's easy to get lost in the notation. Don't. Okay? This is evil notation for an absolutely beautiful concept. Okay? Don't get lost in the notation. All right? The notation sucks. The concept is absolutely beautiful. Okay? This idea that all I did was take an infinite number of rectangles, that I took the limit as the number of rectangles got very, very small. But if it makes you feel any better, this is actually how Archimedes got killed. Okay? So, true story. All right? The Romans are invading Syracuse. And Archimedes, who was, among other things, the most brilliant mathematician that ever lived, okay, built various devices that frustrated the Romans, but finally Roman manpower, they just overwhelmed the city. But Archimedes was this very famous mathematician and engineer, okay? And there were strict orders by the commander that Archimedes should live, by the commander of the Romans, right? The Romans told their centurions, the Roman commander said, this guy we want alive, okay? They wanted him alive. They wanted him to help with Roman engineering projects, okay? So what happened? Well, the Romans came in, they invaded, and Archimedes is sitting there, and Archimedes is thinking about something. So the legionnaire finally finds him. He says, you're Archimedes. You come with me. And Archimedes is sitting there staring at a figure. Right? And Archimedes says, well, we're estimating this, right? Estimati. Area. Rectangulum infinitati. Rectangulum infinitati. Rectangulum infinitati. See. Rectangulum infinitati. Lati. Rectangulum infinitati. Right? Lati rectangulum infinitati. Rectangulum tiny. No. Rectangulum infinitati. Infinitati. Lati. Rectangulum infinitati. Right? So, lati. Rectangulum infinitati. And the Roman goes, quand the fuci. And then goes, stabs him and kills it. Okay? So that's how Archimedes died. He was trying to explain calculus to a Roman centurion. He didn't like that. Now, notice the dates on this. Okay? Notice the dates. Riemann, this is Riemann's formalization of the area under the curve for these functions. Archimedes figured this out. Notice the dates here. 211 BCE. This is before, everybody had to get a new watch because we went from BC to AD, right? This is even before that. And Riemann dies in 1866. 2,000 years separate Archimedes figuring out what to do and someone figuring out what the hell he was talking about. Okay? 2,000 years it took to understand this concept. So don't worry if the notation loses you, right? Again, 2,000 years to figure out what the hell Archimedes was saying. That's how long it took to figure out what the hell. That's how long it took for someone to come and formalize this as Riemann did. Okay? 2,000 years. So don't get lost in the notation. All right? Think about the big concepts. A lati, rectangulum infinitati. Lati, rectangulum infinitati. That's the big picture. Okay? How do we feel about this big picture, 1 to 5? One to 5. Again, the big picture. Lottie, 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 rectangulum infinitati. It's exactly what's happening. The rectangulars are getting infinitely small. They're getting infinitely narrow. A lottie, 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 rectangulum infinitati. That's the big picture. And don't lose it. All right, we're going to close with a big theorem, which we aren't going to prove. Okay. Here's the big theorem. If f is continuous, then f is Riemann integrable. And the limit as n goes to infinity of right, n equals the limit as n goes to infinity of left, n equals the limit as n goes to infinity of up. Did I call it upper or high? I called it high. Okay. So the big theorem, okay, is the following. It doesn't matter. Okay. In other words, it doesn't matter how I define the integral if f is continuous. These are all equal. If you're dealing with continuous functions, they're happy, they're nice, they're pretty, and it just doesn't matter. Okay? How do we feel about that theorem, 1 to 5? Stating that theorem. Okay? This is the big, it just doesn't matter for intervals if they're continuous. Okay? And we have new notation. By the way, notice something about this new notation that we now have. I can't use x. I used x here, so I can't use x in f of t. That's the difference between the book uses a b there and then uses x. I use x for the upper endpoint because remember this is a moving function, but that means that you have to use t, and the thing will catch up in just a moment. There it is. Right, so I use x here, and because I use x here, I can't use x here. Because I use x here, hence I use t. All right. Any other questions, comments, issues, suggestions, thoughts? Okay. So today, this thing's going to take a moment to sync. I'll come it back. I'll bring it right back as soon as it's done syncing. I don't know what's the deal with the internet today. But today we went over Riemann sums and the formal definition of the Riemann integral. And then we just did the integral notation for AUC. Okay. There are more general forms, but everything uses the Riemann integral as a starting point. Okay, so the more general forms of the AUC, things like the Lebesgue integral, they're all equal to the Riemann integral where f is continuous and where f is Riemann integral. What we're going to do, the big ideas, I fixed the top endpoint x. Then I made a lot of little rectangles and I added them all together. The limit, then I took the limit as n, the number of little rectangles goes to infinity. Again, don't get lost in the notation. Think about the examples. There'll be examples on WebAssign for you to do. There you go. And then if it turns out that if f is continuous, then everything is pretty, everything is happy. There is this thing in the textbook that talks about partitions. If you feel so inclined to go down that particular rabbit hole, you may. It's not required. I'm not doing it. If you, again, for textbooks, they kind of just throw the kitchen sink in when they do them. There is an alternate thing you can talk about partitions. If I find another instructors using videos that talk about partitions, I will post them. Are there any other questions? Okay. So as I said, I apologize for not doing the going over the quiz. You need to watch the 9:30 for that. And people that watch the 9:30 video, because I ran out of time so horribly because everything broke, need to watch this video in order to pick it up. Okay. Thank you very much. I now have office hours.